heat, or this is when you talk about intensive terms. If I talk about extensive, then I will say kilojoule into kilojoule per Kelvin. So I will multiply it by what is the mass of the system. That will become capital CV. Everyone is fine with that?
Yes, sir.
Okay. So moving on to go to CP now, I also need to define another property which is called enthalpy. Okay, enthalpy is written as H. So it is you can write again for intensive or extensive terms. So generally we'll try to stick to intensive in intensive terms so that it is more general. We don't depend on mass. So enthalpy is defined like this. Okay, so this is the definition. Enthalpy is equal to U plus PV. Now we know from first law that dq is equal to pdv plus dq. This is coming straight away from the first law. Remember we discussed different forms of first law. Let me just go back. Yeah. So we discussed different forms of first law, whether you want to write in intensive or extensive terms, and we can use any form which is suitable for that particular example or which solves our purpose. Okay, so coming back to enthalpy. Now, this is what we are getting from first law. So I can also write for PV. Let us focus on this term. So I can say that d of PV is equal to PdV plus VdP. This is basically differentiation by parts. Okay, stepwise differentiation. Now I want to get this. So what I'll do is I will take it to LHS, and for a constant pressure process, I can say that dPV is equal to PdV plus this term will become 0 because dP is 0, right? So for a constant pressure process, I can say uh, dq, this equation is equal to, so instead of writing PdV, I can write d of PV. And here I forgot to mention that P is equal to 0. Okay, I'm not able to write it very clearly. Let me write it again. So when I write in this form, I am assuming that dP is equal to 0 or P is equal to constant. That's why I am removing this term. Okay. Then I can take this inside the bracket. So I can write P of PV plus U. Okay. So finally I end up with dq is equal to dh. So what you can say, what you can make a general comment about this statement. You can say that if you have a piston cylinder arrangement, you supply some heat, let us say dq at constant pressure, that heat will be equal to dh. That whatever amount of heat supplied, that will go to increase the h, enthalpy of the system. Okay. Similarly, for the last slide, I can say if you take a constant volume cylinder, okay, if you hold the volume to be constant, let us say I put a screw or something here in this piston. So whatever heat was supplied to the piston at constant volume, that is going to increase the internal energy of the system. Okay, that's why we write for a constant volume process, dq is equal to du. Whatever the heat supplied is causing the change in internal energy. Similarly, whatever the heat supplied at constant pressure, okay, P is equal to constant here. The piston will move, and P is the only one which is constant. That is going to increase your enthalpy H. dq is equal to dH for constant pressure. Okay, so this subscript here, QP, means that it is happening at constant pressure. Fine. So it can also be written like this. This is how it is defined. So instead of PV, I can write RT. Okay, what we see here is, as we have discussed earlier, U is dependent on what? What is the only parameter that U is dependent on? What is the property?
Temperature, sir.
Temperature.
Temperature. So we know that U is dependent on temperature, and again RT will also depend on temperature. So we can say that H is a function of temperature only. So it is a system property and it does not change with, let's say, volume or pressure. It only depends on temperature. Okay, and it is a property. Fine. Now let us come
Sir,
to, yes,
sir, is there any difference between enthalpy and heat?
heat is okay. Enthalpy is a property of a system. Heat is what is supplied to the system. Heat is the boundary phenomena. Enthalpy, I can say that this system has this much of enthalpy, or what is the change in enthalpy of the system. I cannot say change of heat of that system. Okay,
Okay,
like
sir.
internal energy, U. So U, U is the property of a system. Similarly, H is also property of a system defined by this.
Okay, sir.
So they are different properties. Don't mix. For enthalpy, just remember this: H is equal to U plus PV. That's all. Enthalpy is, or in other simple terms, you can imagine that you are heating a vessel, a system with constant pressure. So the heat supplied will cause a change in enthalpy. Whatever the heat supplied will be directly linked to enthalpy. dP is equal to dQ is equal to dH for constant pressure. Okay.
Yes, sir.
Now go to CP.
सर
Yes.
सर इन दिस आपने एंथैल्पी का जो सिंबल है वो स्मॉल एच बनाया, तो सर ये मतलब पर यूनिट मास है?
Yes, it is per unit mass. You can also write capital H. So capital H will be it will be including mass.
ओके सर.
Okay.
यस सर.
So all generally what I told, most of the symbols will try to talk in terms of intensive. But if you know the system mass, you can just multiply by m and you will get extensive properties. But in general, it is more easier or more standard to keep it in terms of intensive, so that once you derive some equation, it is applicable to any system, whatever mass it has. Okay. So now let us talk about CP. So CP can be defined as del H by del T at constant pressure. So we have discussed in the last slide that if your pressure is held constant, whatever heat you supply, that gets converted to dH. So I can say similarly what we did for CV. So if this is true, then I can say that delta H at constant pressure is equal to CPDT. Integrate between the range of temperature that you have. Now dq by p, dq at constant pressure. So that's how we defined in the last slide that if at you supply heat at constant pressure, that will increase your enthalpy. And since we are talking about a constant pressure process, so evaluate CPDT. Okay. So similarly, like delta H, we can also write for delta Q that if you have a constant pressure process, delta Q is equal to CPDT. So again, Cp is a property of the system and it has this value for air. Okay, 1.005 kilojoule per kilogram. So again, this is an intensive. If it will be extensive, capital C, then it will be 1.005 kilojoule for 1 kilogram of air, kilojoule per Kelvin. Now it is intensive, so it is kilojoule per kilogram Kelvin. Okay. Now another important property that I wanted to define, this is called gamma. This is the ratio of specific heats. Okay, which is 1.4 for air. So it varies for different gases, but for air, generally will take 1.4. Okay. Now let us talk about enthalpy and heat, how these are related. Okay. So enthalpy is equal to U plus PV. This is how we define enthalpy. Okay. Now I can write, to differentiate it, I can write dH is equal to du plus PdV plus VdP. Okay, so this differentiation of PdV will give you these two terms, du plus differentiation of PV. Now, if I rearrange it, I can write in this way. For a constant pressure process, I can write du plus PdV is dq, and since the pressure is constant, so this will become 0, so I have 0. So we can say dH is equal to dq for constant pressure process. That is what we assumed in the last few slides, and this is how we can numerically show it to be true. So we can say that dH is equal to dq for constant pressure process. Fine. Is it okay to everyone?
Yes, sir.
Yes, sir.
Moving on. So we'll define a machine which is called perpetual motion machine of the first kind. So we'll study two kinds of this machine. Let us talk about the first one, which is PMM1. Okay. So generally, when you in thermodynamics, if you look at any device or any machine, or let us say any engine, when we talk about, this is the general form, or this is the usual way in which all devices operate. So basically, what happens is that this is your device. You supply some energy to the device. Okay, using this energy could be of any form. Generally, we'll say that heat is supplied, but it could be any form of energy. So this is your input. What input is given to that device? Now, provided that input, that device will work. It will provide some output. So the output is work, and it will have some losses. Okay, so you will not have all work and no losses, but because of friction, let's say some heat rejection, we'll see some losses are there. So this is generally how a typical machine will work. Typical thermodynamic device, engine, or any other machine, this is how it works. Now what happens for PMM1? Okay, so this is a special kind of device. What happens is that it requires no energy input. No input is required, but it still gives output. It still provides work. Okay, so do you think any such device is possible? I don't provide any input and I get continuously get work from this. Will
No,
it
No,
be
sir.
possible?
sir.
No, sir.
Okay,
No, sir.
so the typical characteristics of PMM is that it produces work without receiving any energy. Okay, and it basically violates the first law. So because of that, any such device is not possible. Okay, so it is not that. Basically, when we historically, if you look at development of first law, there were claims of many engines or many devices which could move perpetually. Okay, which could, once you start the motion, it will keep on moving. So that's why they named perpetual motion machine. So initially, a lot of engineers or scientists claimed to have designed this device. So that time, first law was not there. Now, when we formally define the first law, we can categorically tell. Okay, earlier there is no first law, so people could not define what is the problem with such a machine. Now we know first law talks about conservation of energy, so we can very clearly point out that if we have any machine of this type, it will violate the first law. So it is not possible at all. Okay, moving on. Now let us talk about how do we apply first law to an isolated system. Okay, so let's say this is the system and it is isolated. So for isolated system, the same first law will be applicable. With what form we have used for open system, what we are talking about is a closed system only. So, but for an isolated system, there is no heat transfer. Okay, you cannot transfer any heat to a system which is isolated properly. And let us say this is a closed and isolated system, so there is also no work done. So what we can say is for an isolated system, internal energy is constant. You this will not change with time. Okay. So let us now look at how do we apply first law to the closed system? Okay, we have derived theoretical results. We have worked on historical development of the first law. Now let us look how we can apply it to a practical system. How we are going to use the first law for numericals, or what type of problems we'll see in practical cases concerning with the closed system. Okay, so let us say I have a piston cylinder arrangement and I supply some heat Q to it. Okay, one point I wanted to repeat here again, that most of the examples I will take a piston cylinder arrangement. So this is a very typical thermodynamic setup, that we have a closed system, it could move, but generally whatever laws or whatever principles we are talking about, they are applicable to any system, any type of system, any thermodynamic device. But it is easier to talk when you have a system like this. But don't get confused, don't think that it is applicable only to this, it is applicable to all devices. Only thing is, it is easier to discuss when we have a system like this.
Sir, can the piston cylinder system be isolated?
Yes, we can put an isolation around it.
So, sir, in the previous slide, you said
Yes.
that dW will be 0. If we take a piston cylinder arrangement here, then
Okay.
dq will be 0 and work will not, matlab, if it moves, work will not be 0. And so
Yes.
we,
So that's why I have shown a closed box. So there is no piston here. It is a fixed volume box. So for that, you cannot do any work. You cannot like change the volume because it is fixed. And then heat transfer is also not there. That's
so
why I'm.
what if I take that piston cylinder system?
So if you take a piston cylinder system, then you can do work on that.
Won't it violate the first law?
No, why it should? So if you do
Acha, we can do work. Okay, okay. Sorry, sir.
then it will yeah. So see how you define isolated system. For isolated system, my only condition is that I cannot get heat transfer from that system. Okay. So if you do work, it will change in U. So this total of this will be 0. LHS will be 0. So that how you balance this, that is all will decide. Fine.
Okay, sir.
Okay. Moving on. So we have a piston cylinder arrangement. I supplied some amount of heat Q. So what could happen? What are the process that can take place? We'll consider three standard results or three standard processes. So once we heat a cylinder arrangement, then we could have an isochoric process. What is isochoric? Volume will remain constant. It will get heated up, but it will not move. That could happen because of various reasons. Let us say we have increased the force here, or we have pinned it. We can put a screw here and hold the piston at the same place. It could also be a closed box which has fixed volume. So however it happens, but let us say we have an isochoric process where volume remains constant. Similarly, we can also have an isobaric process where the outside force is constant, so the pressure inside the piston that remains constant during heating. So it will expand a little bit, right? We could also have an isothermal process. So we can say that the piston gets heated up, but because it also started to expand, so we are able to maintain the temperature constant, or we can able to achieve isothermal process. Is this clear to everyone? What are the three processes I'm talking about?
Yes, sir.
Okay, so there could be other processes also. I just wanted to give what are the possible scenarios in some standard processes in terms of some. These are the processes we can consider. Okay, so let us see what happens, or how do we apply the first law for these typical examples. So for the first process, when it is isochoric, so work done will be 0, right? In that case, whatever heat supplied, that will change your internal energy. Okay, so this equation, we need to just look at the different terms of this equation, and here we see that W is equal to 0. So I substitute that in this and we get Q is equal to delta U. Similarly, for isobaric, I say that Q is equal to W plus delta U. So both it is doing work, and since it is isobaric, temperature will also change. That will give rise to delta U. Okay, so for an isobaric, you need to write the complete equation. Now, what about isothermal? Isothermal means delta U will be 0. U is only dependent on temperature, so U will not change. Now, in this case, we see whatever heat is supplied, that is totally getting converted to work. Okay, so you can have two extreme. One is that whatever heat is supplied is totally getting into delta U, or heat is completely getting converted to work. Okay, and this is something in between. So heat is getting converted to both work and delta U. Okay, any questions on this? You people are can you hear me?
Sir,
Yes, sir.
Yeah.
Yes, sir.
Yes.
this are possible in real life.
Yes. See, one thing is there that these are all idealized processes. Okay, so when we go to real cycles, you will see that if you talk about isobaric, there will be some change in pressure. So these are very idealized processes. So when I assume isothermal, it is there, it is possible. Which particular example you are concerned about? So when we talk about in standard terms, we say that this is possible. This is how I will apply my first law. So any out of all these three, any one which you are not happy with or you have questions, please tell me what process you want to discuss. Yeah, can you hear me?
Yes, sir.
So
Yes, sir.
someone was asking.
Yes, sir.
Yes, sir.
Okay, someone asked if you are clear, then we'll move forward. So let us take
Oh,
some numbers. See this again. I will stress here that this is the theoretical foundation. Once you start doing numericals, then only you will be clear with how these things work. So that's why I will strongly suggest. That's why I'm not giving you solution. I will give you solution at a later time. Right now, I want you to solve that practice problem so that you are clear with what numbers are there, how do we apply first law or any other law for a particular system. So you should do it yourself, struggle with the problem, and then you will learn. Fine. Okay, let us now take some numbers. Let's say that for these processes, let us say Q is 100 kilojoule. We have supplied 100 kilojoule to the system. Okay. Now, let us see how it gets divided. So for isochoric process, delta U will be 100 kilojoule. For isomeric process, we know that the total is this much. We need to further find out how much will be how much work is done and how much changes internal energy. So this we can use Cp. So that will come to, but the idea is that once you apply first law, then the sum of work done plus internal energy is equal to heat supplied, which is 100 kilojoule. Similarly, for isothermal process, work done is 100 kilojoule, total amount of heat supplied. Okay, now this is an interesting process. So when we go to second law, we will see that in a cycle you cannot convert heat to work. Okay, this is generally not possible. And for a cycle, it is not possible at all. But for an isothermal process, isothermal is an idealized process. There you can achieve this. Okay, but not in a cycle. This can happen for a process. There is one process we heated it and it expanded and work is done. But if you take a complete cycle, then total it's applied will not never be equal to work done. So this we'll discuss in more detail when we go to the second law. Fine. Any questions up to now? Okay, let us move ahead. So now, till now we are talking about first law for closed system. Now we'll look into open system, how we can apply the first law. So let us ask a very basic question, whether we can apply first law for open system. Okay, for closed system, we let me draw it. Okay, so for closed system, we can call it a control mass. Okay, so we have a mass which is bounded by the system. So we can have all type of heat transfer, work transfer, and we can analyze. We have this mass is under control. This mass is fixed. Okay, so we can do all type of analysis using the system. Now let us say I have a nozzle. Okay, so air is flowing in, air is flowing out. Then the mass could also change. Air could, let us say, the velocity will be something here at the inlet, velocity will be something at the outlet. So will the first law will still be applicable? What do people think, or not?
Yes, sir, it will be applicable
Yes. So that
because energy will be conserved.
correct. So whatever the type of system you have, first law will always be applicable. Okay, but we'll see how we apply that to an open system. We'll take some simple examples and then we'll see how we'll talk about mass balance and energy balance, and we'll try to see how the first law is applicable or how it can be used to make calculations for an open system. Okay, so let us first define steady and unsteady processes. So steady process is a process where properties remain constant with time. Okay, the properties or flow variables can change with space. So it could be different property when you go downstream, but it has to be constant with respect to time. Similarly, for unsteady process, properties change with time. Let us say your density is changing with time, velocity is changing with time. So what I can say in simple terms is that you take any variable and you do a differentiation with respect to time. If you get 0, it is a steady process. If you don't get 0, then it is a unsteady process. I hope this is clear to everyone. Right? So based on that, we'll derive equations. We'll derive governing equations for open system based on whether they are steady or unsteady. Okay. Now let us take a very simple example. Okay. Let us before developing formal equations, we'll take a very simple example. Let us say this is your water tank. Okay, water tank what we have in your room. So what happens in a water tank? You have some inlet pipes, you fill water, and then we have outlet pipes where we take out water from that. Right? Let us say it has 2 inlet pipes and 3 outlet pipes. Okay. Let us say I know the flow rates also. Inlet, let's say it has 6 and 5 kilograms per second. This is the rate of water which is pumped in. So we have 2 pumps. One is sending water at 6 kilogram per second. One is sending us 5 kilogram per second. Now let us talk about the outlet. So these are the flow rates from outlet. So this is connected to a tap, and this is, you open all the taps, and this is what is coming out. Now the question is whether this process is steady or unsteady. So how can
It is so.
Steady.
so why do how do you know that this is steady?
The height is
No
not
mass
changing.
is
So
changing.
Yes. So if you look at the inlet and outlet, So what I need to do is I need to take the sum. If you add what is the total inlet? Total inlet is 11 kilogram per second. Total outlet is also 11 kilogram per second. So basically, the level of water will not change. Whatever is the same amount of mass is leaving the system. So then we can say that the system is steady. Okay, now let us talk in terms of variables and then we'll derive this equation. Derive equation for mass balance. Okay. So let us say instead of giving the numbers, we have m dot 1. See, m dot is rate. M1 could be mass, but m dot means kilogram per second, rate of mass flow. So m dot 1 and m dot 2 are the inlet mass flow rate for two different pipes. So you could have one inlet or three inlet, four inlet. Just to keep in some general terms, I am referring to two inlets and three outlets. So we have, these are all outlets. So mass is leaving the system. Okay. Now we need to, for open system, we need to define a control volume. Remember we discussed in initial classes that we need to define a suitable geometry for control volume. So what will be the best way to, or the best suitable option for control volume? Anyone want to guess? Can I make a control volume like this? Can I take this shape or not?
No, sir.
Anyone else? I think I can take this shape. You can define a control volume of any arbitrary shape that you like, but it will make your analysis difficult. Okay, so we can take it, but we will not take it. Understand the difference? It is not that this is not allowed. The problem is that it will make your analysis difficult. So the most easiest or most convenient way to define the control volume would be this. So we take the volume of this tank as the control volume. Okay, but there is no rule or law which says that this one should be your control volume. I can take even half of this volume and say that this is my control volume, but it will not be convenient. It will not be easy to work out numericals. Is this clear to everyone?
Yes,
Yes,
sir.
sir.
Fine. So now we'll go ahead. So we'll talk about this M. Let us say initially we have MCV. This is the mass which is contained inside the control volume. Now let us say how this mass of control volume changes with time. Okay. For example, you can imagine that we have some water filled and how that level changes, how that water is increasing or decreasing inside the control volume. So what we can say is that M1 and M2, these are adding to the mass inside. If you close all this will keep on increasing mass. Okay, so this will be positive, and the remaining terms, which are outlet terms, that I will write as negative. So I can say that for, if I want to calculate the change in mass of control volume with respect to time, I can take the sum of these two terms. I can say that this is all inlet terms which are positive, and these are all outlet terms which are negative. Is this clear to everyone?
Yes, sir.
Yes, sir.
So I can also write in this way. I can take summation over all inlet mass flows and outlet mass flows. So this is called conservation of mass or continuity equation. Okay. Now this equation, if it is unsteady, Unsteady means this will not be 0. Then this will not be equal to this. Inlet will not be equal to outlet. What it means is that water level in a tank will keep on changing. It could rise or it could decrease, but inlet is not equal to outlet. This is unsteady. While we talk about steady terms, okay, so that time we say that these two are same. So the level of water is remaining constant in that system, constant in that tank. Fine. So for that, if you could take a very simple example, okay, let us say there is only one inlet and one outlet. Then, and we know, let us say we know the density, we know the cross sectional area, we know the velocity. So these three things we know. M dot will be equal to rho AV. So if we have one inlet and one outlet, then I can write, let me get a pen. Okay, so then I can write M dot 1 will be equal to M dot 2. 2 is what is exiting. So if it is a steady system, steady process, such that the mass inside this tank is not changing, level of water, to keep it simple, you can think about level of water, but generally it is, this equation is applicable to any liquid or any gas is there. It is not only for water, but it makes it simpler to understand. That's why we are referring to level of water. So if we have one inlet and one outlet, so if I want to maintain this constant, this is basically MCV. Okay. So if I want to maintain MCV constant, I will say that M1 is equal to M dot 2. Now M1 I can write in terms of rho AV. So I can say rho 1 A1 into V1 is equal to rho 2 A2 into V2. So in your numerical problems, generally you will have these variables. You will be having the values of density, velocity, and area. So you can just equate that and get the, let us say you need to find what is the velocity at the exit for a given parameters. So then you can use this and calculate. Fine. This is my CV. Okay. Now I will leave you with a question. So let us say this is the system we have, and let us say that each of these flow streams, okay, so there are different inlets and outlets. Each of them have some associated specific heats, internal energies. Okay, so this is E is for total energy. If I write U, it will become internal energy. So each of these different streams have different energies that is coming inside. So this is the form of equation I wrote for mass balance. I said that d by dt of mcv is equal to difference between inlet and outlet. I took the summation of inlet and outlet and subtracted that. Now the question is whether can I write energy balance equation? Okay, so this is, I can talk about ECV. What will be ECV? EC will be the multiplication of this. Okay, simply I will take ECV is equal to MCV into small e. Small e is intensive. Now we're multiplying with mass and making it extensive. Okay, so we talked about mass in that in this form. So can I use the same equation or similar type of equation to calculate change in energy? Is it correct or is it possible to do? Or if not, what else is required?
Possible, sir.
No,
Yes, sir.
sir, this
Yes,
is
sir, we
not
can.
correct.
Possible,
What
sir.
about,
Energy conservation.
what about work and heat transfer? Okay, so we could maintain the same form of equation, but we also need to consider heat transfer and work transfer. So this will be the additional term, but we need to add some terms to account for heat and work transfer. Fine. So this will look at in the next class. We'll stop for today. Any questions on what we've discussed so far?